Good morning and welcome to Algebra 1. Today we're starting a new unit called Systems of Equations. Here's what's meant by a system. More than one. If you have more than one equation to graph at the same time, you can call it graphing a system of equations. We could also solve a system of equations algebraically without graphing. To solve a system of equations is to find out where the lines will cross. The coordinate where they cross, that's what we call the solution. So there are three ways to solve. We're going to cover two right now. The first method of solving a system of equations is with graphing. So I'm going to quickly open the pantry door because I think my cat is trapped there, and then I'll show you how to graph. Just hold on one second. Turned out she was trapped in the basement. So, back to the work. When I graph a system of equations, I can see where two lines will cross. Now, graphing is not a good method. It's really easy to have inaccuracies, and if the lines don't cross exactly at integer coordinates, you're never going to know what the solution is. And yeah, the solution could have fractions or decimals. You're never going to be able to tell just from a graph if it's got decimal or fraction coordinates. But I'll give you one that doesn't, and we'll see how it works. Sometimes we are asked to graph. So here's the first one. I'm going to put up a little grid paper. I don't know if the grids are easy to see on the video, but I can see them. So we are going to give you a cross here. So we'll go here, and we'll say there. So there's your coordinate grid. I'm going to give you two lines, and they're the lines y equals 2x minus 1 and y equals negative x plus 8. Now, they are two linear equations. So we should be able to, without too much stress, graph them. If we could find out where they cross, we found the solution. The first one has a y-intercept at negative 1, and it has a slope of positive 2, so it goes up 2 over 1. And I'm going to just try to connect that as best I can. Okay. Give myself enough points so that a shaky hand could still graph somewhat straight. Okay, the other one has a y-intercept of positive 8, so we have to go up to 8 on the y-axis. Hopefully I have enough room. 2, 3, 4, 5, 6, 7, 8. Yeah, I do. And it has a slope of negative 1, so it's going to go down 1 over 1. If I keep following it out, I do see where they cross because I put enough dots on this thing I could tell where it's going to go. And then we would graph that line. Not the world's best graph, but you could see that it crosses right there. Now that's the coordinate 1, 2, 3. 1, 2, 3, 4, 5. So the solution to this system is the coordinate 3, 5. If you want to double check it, you want to plug in the 3 to both of the equations and see if we get a 5 each time. So if I plug into the first one, y equals 2 times 3 minus 1, well, that's 6 minus 1, which equals 5. So it works there. We also check the second equation, y equals negative 3 plus 8. Well, negative 3 plus 8 does equal 5. So it checks out. We got our solution. Now again, graphing is not a great way to go. We're not going to focus on the graphing way to solve a system because for so many reasons, it's just ineffective. So I'm going to not graph anything else for right now. So far, hopefully everyone understands A system of equations is one in which two or more lines are drawn, and the solution to the system is the place where those lines are going to cross. If we have parallel lines, they don't cross. So a parallel system has no solution because there's no place where it crosses. What if I graph the same line on top of itself? Well, that's obviously the same line graphed twice, and that's got solutions everywhere because it crosses itself everywhere. That would have infinite solutions. Let's keep that in mind for the near future. Now, I'm going to solve the next system with a different method. It's called substitutions. It's far more mathematically reliable. So, what is the substitutions method? Well, to make it nice and simple, you're going to substitute something in place of one of the variables so you can solve. Here's an example. We have two equations. Y equals 1/2 x plus 4. And also another equation, which isn't even in slope-intercept form, 2x minus 6y equals -14. We don't need them to be in slope-intercept. We don't need them to be in standard. We just need them to be workable. Here's what the substitutions method does. If you can isolate one of the variables, you could then substitute that quantity into the other equation. You can't solve a problem when there's two variables. We've got to solve for one first. Now, in this equation, I could get the x by itself or I could get the y by itself. It's your choice. But I don't have to do either one of those two things because I could also work with that equation right here. You might notice it already says y equals. It's perfectly set up for substitutions because I can take this quantity of 1/2 x plus 3 and substitute it in place of the other equation's y value. Remember, what we're looking for is where they equal each other, where they cross. So that's got to be the same coordinate for both equations. If I plug this in, called substitutions, to where the y was, I am able to solve the problem because now there's only one variable. It's the variable x. I can solve that. So let's distribute the 6. So we have 2x minus, well, what's 6 times 1/2? 6 times 1/2 is 3. So 3x minus -6 times 3 is minus 18 equals -14. 2x minus 3x is just -1x or -x. I'm going to add 18 to both sides also. Adding 18 to both sides gets me a 4 right there. Divide by -1. X is -4. So we already have the x value of the solution because I know where they're going to cross. They're going to cross at -4. Where? Well, you see this equation that says y equals? I got to solve for y now, so let's just plug that on back in. Y has to equal 1/2 of -4 plus 3. 1/2 of -4 is -2 plus 3 gets you 1. The place where this system of equations will cross is the coordinate -4, 1. If you're not sure, you can always double check it. If I plug in a -4 for x, do I get a 1 for y? Well, I just did that over here, so I'm pretty confident, but 1/2 times -4 is -2, plus 3 is 1, which it needs to be. In this equation, if x is -4, 2 times -4 is -8. If this y is 1, -6 times 1 is -6. -8 minus 6 equals -14. It works fine. The method for substitutions is algebraically reliable. Yes, in this example I gave you, there is an easy-to-locate graphable solution, but that won't always happen. So Substitutions better than eliminations. I'm sorry, better than graphing. Eliminations is the third method, which I haven't talked about yet, and I'll talk about that at a later date. But we like substitutions better than graphing. Most people don't enjoy graphing anyway, and if you don't have graph paper, it makes life a lot easier to not have to graph. So here's what I want to do. I'm going to give you your 3 homework prompts. I would advise you solve all of them with substitutions. So here's the first system. We got x plus y equals 4 and negative 3x plus y equals 12. For this one, you're going to have to isolate the x or the y. I wouldn't necessarily pick this x because you have to divide by 3, which would give you a fractional y. But this is pretty easy to get x or y by itself. You don't have to do y, or you don't have to do x. It's whatever's easier for you. The second system is y equals negative x minus 8. That one's in slope-intercept. And 3x plus 2y equals negative 20. That one's in standard form. And the third prompt you have to solve, y equals 1/3 x plus 2 and y equals negative x plus 10. They're both in slope-intercept. This is the homework, so please make sure you get this done and sent it to me no later than tomorrow morning at 7 a.m. Join the live meet if you have any questions or want to see further examples. Send me an email if you have any questions. Have a great day. I'll talk to you soon.